Hello there. Today I want to tell you about a fascinating story in the universe. When I was about 15 years old, maybe 14 or so, my cousin came up to me and he said, "Have you heard the news?" And I was like, "What news are you talking about?" He said they discovered gravitational waves. And I was like, "What are gravitational waves?" So I did not know what gravitational waves were back then until I did some research, and it turned out that gravitational waves are a result of Einstein's theory of general relativity, of gravity. And gravitational waves are movements in space. Space moves, ripples, and vibrates, just like when you throw a rock into a pond of water. Waves are resulted from that action. What are these waves of space? This is what I have prepared in this video. I have interviewed one of the leading physicists in the field of cosmology and astrophysics, Dr. Niayesh Afshordi, and I have asked him a few questions that would help me and help all of us understand the physics behind gravitational waves, how are they originated, and how they can help us understand the universe and its beginning. So, let's see.
Okay, very good. So I am here.
Okay, let me just start recording.
Yeah, sure, go ahead. I don't see you. What happened to your picture? Ah, there you are. Okay, very good. Your beard is new, is that right?
No, it's old. It's been there for a long time.
You always had a beard?
Yeah.
I don't know. But I've seen you before, right? We've met before in person.
Yeah, during the FIS10 lecture. Probably
Yeah.
not as much, but I grew it now a little bit.
I see. So maybe it was not. Okay, so that's why I cannot recognize.
Yeah.
Let's see.
So I'm gonna start with like an introduction about yourself,
Okay.
and then we can start with the questions. So Dr. Niayesh Afshordi is an astrophysicist, a cosmologist, and a professor at the University of Waterloo. He is part of the Waterloo Center for Astrophysics and also a researcher at the Primordial Institute for Theoretical Physics in Waterloo in Canada. He obtained his bachelor's from the Sharif University of Technology in Tehran, Iran in 1999, and then he went on to earn his PhD from Princeton University in the United States in 2004. He was awarded the Buchalter Cosmology Prize twice. In 2015, he came in third place for his work on cosmological non-constant problem, cosmological bounds on tera-electron-volt scale physics and beyond. The second one that he received, he came in first place in 2019 for his research Echoes from the Abyss, a highly spinning black hole remnant for the binary neutron star merger. He was also awarded the Professor M.K. Vanu Bapu Gold Medal from the Astronomical Society of India in 2011. Dr. Afshordi is interested in studying the mysteries of the universe, ranging from dark matter and dark energy to black holes and gravitational waves. So, welcome, Dr. Afshordi. I'm really happy to be having this interview with you. You've been one of my heroes, and I'm always interested in your work and research. And I think your paper, Echoes from the Abyss, is a masterpiece. I have it on my wall. I always try to study it and understand it fully, but it seems complicated at parts. But I'm willing to do the work.
Thank you very much for the introduction. I mean, I don't know what to say to that introduction. It was, I think you might be making it making more of it than you should, but I do appreciate the attention, let's say, and yeah, I mean, I'm happy to talk to you.
Right. So the first question I have for you. How did the concept of gravitational waves come to be, and what is meant by gravitational wave?
That's an excellent question. So, gravity, as you know, I mean, originally it started from, I mean, of course, understanding the motion of objects around us. I mean, Galileo thought about gravity and the uniform acceleration. Everything that falls has the same acceleration. And then Newton kind of developed this for motion in the solar system. But gravity as it was understood for most of human history as a force that pulls us towards Earth and then pulls celestial objects towards each other. But then in early 20th century, when Einstein came along, basically almost a century ago, almost exactly a century ago, he tried to unify gravity with other laws of nature as we know it in the form of basically relativistic formulation, because before that he had realized that electromagnetism, if you want to make sense out of it, you need to change the notion of a space and time. So electromagnetism, but if you want to go back to the history of relativity, it was partly for understanding electromagnetism and partly to understand why the speed of light doesn't seem to change when we move, because the speed of other waves seem to change when we move with respect to some medium. But it seems that light didn't have a medium. And from there, we Einstein taught us in a special relativity that there is no ether, and at least no ether for light as far as we can tell, and time is relative, so there is no absolute notion of time. Different observers measure different times. But what became complicated was when he tried to add gravity to this basic system, because it seemed that gravity could propagate instantaneously, and it didn't make sense in relativity because nothing can go faster than the speed of light in a special relativity. So there must be some field like electromagnetism that transfers gravitational force. But the weird thing was somehow, no matter what objects were made of, they accelerated the same way or reacted the same way to gravity. So unlike electromagnetism, where it depends, like neutral objects don't care about the electric field, but charged objects do care about electricity. For gravity, everybody does the same thing, which is weird. So it makes gravity different. Of course, you could have imagined that gravity, there's another force, another field that transforms or conveys a gravitational force. But this gave Einstein an idea that maybe the field that transmits gravitational attraction is different from other fields. Maybe it's more like geometry that is independent of the object. All the objects see the same geometry. So that was the key idea, that gravity, and it really goes back to Galileo, that everybody accelerates the same way under gravitational force. But then basically the key insight of Einstein was that maybe it's the geometry that's responsible for that. So the reason everybody accelerates the same way is that everybody responds the same geometry. And free-falling objects basically try to move on straight lines, but they see a curved geometry, and everybody then reacts the same way, no matter what they're made of. So that's Einstein's equivalence principle, and based on that, he developed a geometric notion for gravity. So it's not a field, but it's rather geometry. And then he developed his equations. Now, that was the first step. That was the birth of general relativity. And then our mission for the past century has been to understand the solutions to these equations that Einstein wrote basically in 1916, that they looked simple, but really they had a really complex life, took a life of their own. And one of the things that, in fact, Einstein didn't anticipate was that you could have waves of gravity. So these equations that he wrote did whatever they wanted to do. And one of them was, they don't just transmit force. You could, in fact, have gravitational waves in vacuum, even if there is nothing there. You have empty space. So gravitational waves are really waves of geometry that propagate in space. Now, you usually need something to make them, because at the end of the day, things that are perturbing the geometry are matter. But then these waves, when they're generated, they can propagate in vacuum and then move far away, much, much farther than gravitational force can travel.
So the second question I have, so you mentioned that gravitational waves are propagations of space, right?
Of geometry of a space, yeah.
So does that mean space is not static? And what does that mean in terms of the expansion of the universe? Because as we know, the universe is also moving in a way and getting bigger and bigger.
No, that's an excellent question. So, and now what does it mean for a space not to be a static? It's now one of the things we learned from Einstein is everything is relative. Well, at least some things are relative, and one of those are the notion of a space and time. So whether a space is a static or not a static, in fact, is not there's no clear-cut answer to that in relativity. It could be a static if you want it or not if you don't, because in fact you could choose whatever set of observers who you want, that you want. So your observers could be moving away from each other, or your observers could be sitting basically at constant distance from each other. That's the choice of the observers. You and I could decide to sit in a room, but another observer could decide to travel into the space, right? So that's their choice. But then you could ask the space in which these observers are traveling, how does the geometry of that space evolve? And for example, we have LIGO detector, which consists of these interferometers. So there are lasers going through these vacuum tubes, kilometers, basically in these tunnels in either Louisiana or Washington states, and these are kind of fixed tunnels, so nothing is moving there. There are lasers going back and forth, and you would think that's a static situation, but it turns out that it's not exactly the case. There are these waves of geometry that pass through. So even though it looks like these observers or these detectors are static, in fact, the distance between them changes ever so slightly. It's like 1 part in 10 to the 20th. And that changes in distance is, in fact, due to the fluctuations in geometry. And the same goes with expansion of the universe. So expansion of the universe is in some sense is a little bit of a misnomer because you don't really, you could choose, you and I are not really getting farther and farther apart. So we are sitting still, and size of Earth, it doesn't change very much. So expansion of the universe doesn't make Earth bigger, and it doesn't make the solar system bigger. But if you go to very large scales and cosmological scales, it turns out that the galaxies are getting farther and farther apart. And that's the preferred observers on larger scales. So it looks like the cosmological observers, that would be galaxies on larger scales, they are moving farther and farther apart. And we kind of think about that as the expansion of a space, even though it's really the expansion of the distribution of galaxies. So the galaxies are getting farther and farther apart. So at the end of the day, relativity tells us that, everything is relative. But then when you decide on your observers, be it galaxies or LIGO detectors, then relativity tells us a set of rules for how the distances between them changes with time. And on a small scales, that could give you gravitational waves, and on larger scales, it could lead to expansion of the universe.
So speaking of LIGO, you mentioned that Einstein came up with his theory mathematically, and we know in physics that math needs to be proved so it can be true. So were these waves discovered? And if so, how did scientists manage to see these movements of space?
Yeah, so that's very good. Even Einstein at some point didn't believe there were gravitational waves, so he thought that they were kind of some sort of an artifact, they're not real. So he published he wrote a paper that was not actually accepted for publication. So for some time he was upset with that, saying that, or claiming that there are no gravitational waves. And indeed, they are a really weird thing because that's not what you expect of gravity, and he was not setting out to do that. In fact, there are a bunch of things that Einstein was wrong about. He also thought the universe was static. Everything is basically sitting at fixed distance, and he famously call that his biggest blunder. Gravitational waves was another one, which, I mean, it took much longer for that idea to be tested. Expansion of the universe, we kind of discovered about that in 1920s, so shortly after Einstein's discovery of relativity. But yeah, gravitational waves, it took a while to actually see directly. But we've known about gravitational waves for a long time, mathematically, because in some sense, there are so many aspects of relativity that have been tested. And there is, if you think they're all within a consistent mathematical framework, gravitational waves is also part of that. But even going beyond that, emission of gravitational waves have been tested indirectly through binary neutron stars, Halson-Taylor binary pulsar, because the idea was basically these are two close neutron stars, and then they're going around each other, and then emit gravitational waves. We didn't see the gravitational waves, we still don't, but it turns out that the orbit was shrinking. You see that the period getting shorter and shorter over time, and that was consistent with basically loss of energy due to emission of gravitational waves. So we basically believed in it from mathematical consistency for some time, but for the skeptics, there was this Halson-Taylor pulsar that was, in fact, won the Nobel Prize because of their discovery. And then even more directly now, as I mentioned, through these LIGO detectors, and then Virgo more shortly after that. I think the Kagra in Japan is the latest functioning gravitational wave detector that is capable of actually seeing gravitational waves. So the idea basically is that these are these lasers that bounce back and forth between mirrors that are kilometers apart. And because the wavelength of the laser is very short, is our kind of, wavelengths of light is, I guess, of order micron, but the distance are kilometers. So you could have constructive and destructive interference between basically lasers that go back and forth in different directions. So one beam goes in one direction, and another beam goes in another direction. They can go and get reflected and come back, and they could either have constructive or destructive interference. And because the wavelength is so short, if you change the distance a little bit between the two, between the mirrors, you could see a lot of change in the interference pattern, right? Like a micron change in distance, and this is a large distance at kilometers. That's enough to give you, to give you a big effect, and that's how these detectors work, right? So you measure tiny changes in distance due to changes or ripples in geometry.
So my other question is, as we know now that we don't really understand the nature of dark matter, could you explain briefly what dark matter is and if it is possible for them to radiate gravitational waves away?
That's an excellent question, and I mean, I wish I knew the answer to that. The thing about dark matter is we know what it's not, and there are a lot of things that it's not, but yet there are many more things that it can be, just because the possibilities are infinite. The space of the unknown is invariably bigger than the space of the known. We've known about dark matter for, almost 70 years. So originally, what happened was Zwicky looked at motion of galaxies in Virgo cluster, and looked like they were moving at thousands of kilometers per second around through by studying their spectra. But if you just counted all the mass that you could see, that was not enough to account for these speeds, because you would think that things that are moving around fast, they must be bound by large mass. Like for our Earth is going around the sun at 30 kilometers per second, and from that and the distance to the sun, you could infer the mass of the sun, which is around 2 times 10 to the 30th kilograms. You could do the same thing for the Virgo clusters. Those are much bigger scales. Velocities are much bigger. Instead of 30 kilometers per second, you have thousands of kilometers per second. And you infer a very big mass, like 10 to the 15th solar masses. so 10 to the 15th bigger than the mass of our sun. And yet, if you just look at all the stars, trying to count the light you get from the stars, it's like 2 orders of magnitude smaller. So that was originally the idea that maybe there must be something there, some unseen mass or dark matter there that's keeping these galaxies bound together. I mean, otherwise, why would there be just this concentration of galaxies in one place if they cannot be bound together? So that was the birth of the idea of dark matter. And over time, I mean, this was kind of a crazy idea early on. And Zwicky was kind of a crazy person, artist. He had weird behaviors or weird habits or quirks. So not many people took him seriously, although he was a visionary. But over time, people came along and started to believe. I mean, there were other observations, other clusters of galaxies that confirmed this, and then even within our galaxy, with galactic observations, most famously by Vera Rubin, noticed that the rotation of the stars around the center of our galaxy and other galaxies seems to be flat. Basically, the rotation doesn't fall off, even though it looks like there are no there's not enough matter to basically keep things going around as fast as we see them going around. So, and then most recently, understanding the Big Bang and what comes out of it through cosmic microwave background, so basically properties of cosmic microwave background, it kind of made it a slam dunk case, because to really understand and fit the data from cosmic microwave background, you really need dark matter. So there is really no wiggle room left. So there are basically so many pieces of evidence for dark matter, it really makes it very hard to not take it seriously. And any competing model that doesn't have dark matter, they must put some exotic physics, some very weird modification of gravity maybe, that could explain all the observations. Now, what it is made of, though, we don't know, because all we can tell is that there's some stuff which is relatively cold and relatively, dense. There's a lot of it out there, so it impacts gravity. And that's all we know about it. We haven't detected any interaction. There have been dark matter detectors searching for particle dark matter of various forms, and all of them have, with some exceptions, they all have come empty-handed. The ones that the exceptions are kind of controversial, so there might be other effects that they're seeing, and that's kind of the status. That now, whether we could have gravitational waves from dark matter, that's an excellent question. That depends on the type of particle that it is. If you have massive particles like black holes that make up dark matter, then indeed they could merge. When the black holes merge, could emit gravitational waves. So generally, to have more gravitational waves, you need more massive things. So that's possible, but since there's a large range of uncertainty for the mass of dark matter particle, in fact, for first LIGO detection, it was suggested that maybe these are, they could be dark matter, primordial black holes that formed in the early universe through some mechanism. They make up the dark matter, and then when they merge, they emit gravitational waves. Now the numbers don't exactly work out, but still it could be that dark matters that, or there could be black holes of different mass ranges, might make up the dark matter and might emit gravitational waves through mergers.
My next question is, so the universe started with a Big Bang 13.8 billion years ago. Is there a possibility that such a violent event could cause gravitational waves? And what would these waves tell us about the beginning of the universe?
That's another excellent question. And indeed, the answer is yes, there is a possibility. If you have a violent event, the more violent things are, the more likely it is to emit gravitational waves. Mergers of black holes, we know for a fact that it does emit gravitational waves. In spiral of neutron stars, I told you that was the first indirect evidence we had for gravitational waves. Now, the Big Bang is a mystery. Now, what we know about the mystery is universe at early times was very uniform. So that makes it hard to emit gravitational waves, because gravitational waves are kind of stresses in a space. So in one direction, things are being squished, in another direction, they're being stretched. So that's the nature of gravitational waves, that they are these modes of geometry that propagate. They change the shapes of the objects. They don't expand things uniformly or shrink them uniformly. They just stretch them in one direction and kind of shrink them in another direction. A uniform universe cannot do that because it's isotropic. So you need anisotropies or inhomogeneities. We have a little bit of those. That's what we see in the microwave background, and not what's responsible for formation of galaxies. Now, is that enough to give you, significant gravitational waves? On the face of it, not very much. It's not clear. But early universe is very dense. So now the densities are low relative to early universe. So you had things that are very uniform, but on the other hand, are very dense. So you have a little bit of anisotropy or inhomogeneities. That could go a long way in principle. So we don't really know. The leading proposal for getting gravitational wave out of the Big Bang is not through mergers of black holes, although that's certainly a possibility if you have very small black holes. The leading possibility is that because very tiny things stretch to very big things during Big Bang, you could have quantum fluctuations of gravitational waves that get stretched and become very big. And there must be some process that does it. Inflation is one of the proposals, the most popular proposal for what happened in the Big Bang. And in fact, one of the attractions of inflation is that it could take the quantum fluctuations of sound waves on the very small scales, stretch it to very large cosmological scales, and that makes it to basically sound waves that we happen to see in the cosmic microwave background. So in cosmic microwave background, our observations show basically coherent oscillations that plausibly could have started from quantum fluctuations on very tiny scales and then stretched to larger scales through some early time phase of inflation. Now, the same could happen with gravitational waves, and that's one way that you could make them. There could be other ways, as I said, through mergers of tiny black holes or other weird processes that we cannot think about in the universe. For example, phase transitions. You could make bubbles, like the same way that when water boils in the kettle, so you're turning liquid water into gas water or to vapor, and then that's kind of a very inhomogeneous thing. You see kind of bubbles popping up everywhere at the bottom of the kettle and then rise to the top. So that's kind of very chaotic and random, and that's how a so-called first-order phase transition looks like. And the same thing could happen in a real universe, but maybe in the reverse order. You have a hot universe that is cooling down, and then you could make bubbles of a different phase that popping up here and there. And then when these bubbles collide, you could emit gravitational waves. So that's another possibility. So yeah, the early universe is really an open question. Lots of things that could happen, and then some of them may possibly emit gravitational waves.
So my next question for you is, you have published a paper with the title Echoes from the Abyss, Tentative Evidence for Planck Scale Structure at Black Hole Horizons. So I think what you have presented in this paper is revolutionary and crucial to the quest for unifying gravity and quantum mechanics. Could you elaborate on the main idea of the research paper and what data or tools have you used to solve such a mystery?
Right. So let me start with a caveat that this is an observational paper. So we search for evidence for a certain for a central signal. The evidence is not at the level of a detection. So it's the evidence that we think is statistically significant, but it's not a slam dunk. If it is real, then I think it is revolutionary, and you're right to be excited about it. But then it's also you would also be right to be skeptical, because it is something new, and you may require more evidence for it. And indeed, what happened in the past 5 years, I can get to it, shows that maybe more evidence is needed. You cannot just take that on its face value. So our analysis was the first to do it, but there have been lots that followed, and the issue remains controversial. So let me tell you what's the story. So the main question is, are black holes quantum or classical? So black holes are basically, or in fact, you could go even deeper. So there are really two things that Einstein is famous for. Relativity is the one that you usually hear about. But there's another thing that, in fact, what Einstein won the Nobel Prize for. He didn't win the Nobel Prize for relativity because that was, in some sense, too speculative and too futuristic for the Nobel Prize Committee. So Einstein won the Nobel Prize for explaining a photoelectric effect, which basically tells is a signature that light comes in quanta, the quanta that we know as photons now. And it was basically one of their early realizations of quantum mechanics. He's done other works. The one that I've become a fan of recently is explaining quantum radiation, quantum absorption, and quantum emission, which is really the underlying principle for how lasers, for example, work. So that's also Einstein's work. So Einstein really has had a foundational role in development of both relativity and quantum mechanics. But there lies a contradiction that it seems that the rules of quantum mechanics and relativity, even though they're both very deep and they're both very successful in explaining different phenomena, they're not consistent with each other. For example, relativity says that nothing can propagate faster than the speed of light, but quantum mechanics says that there is uncertainty. So you cannot be sure how fast something is propagating, right? So there is always uncertainty principle. Things, if someone goes from here to there, there is a chance that they're going faster than the speed of light, and there's a chance that they're going slower than the speed of light. You can never be sure. So there are these two fundamental principles that are in contradiction with each other, and you could then go into the calculations and see that indeed, if you try to adhere to both principles, you hit problems and paradoxes or inconsistencies in various places. Usually things become very inconsistent if you go to very high densities or temperatures. So this is known as Planck temperature or Planck density, which is a huge density. I think it's like 10 to the 90 kilograms per cubic meter. Our temperatures would be, when we try to centigrades, it's like 10 to like 26, if I do it correctly in my head, something around that, 10 to the 26 centigrades or so, or maybe 25th. So it's within a factor of 100. I think that's about right. Which is, that's the level of uncertainty we have anyway. So those are kind of exotic situations. So you think, okay, so there are problems there, but maybe we don't care about them because they're not around us. We don't get there. But it turns out that things like that can happen naturally in the universe, and there are two places we know they do happen. One is at the Big Bang, and the other is at the black hole, when you form black holes. So inside the black holes, these conflicts become manifest as does at the Big Bang. And there we have to understand something about quantum mechanics and gravity. Basically, we have to find a good compromise. Otherwise, we cannot really tell what's happening. Now, the case of black holes is interesting because Einstein's gravity tells us that black holes are these surfaces of no return. When things fall into them, nothing can come out because nothing can go faster than the speed of light. But on the other hand, quantum mechanics, as I told you, tells that there is uncertainty. You can never be sure exactly how fast things are propagating. And in fact, Stephen Hawking was the first person who showed this uncertainty of quantum mechanics is responsible for evaporation of black holes. So even though you think nothing can get out of black holes, quantum fluctuations of fields and stuff around black holes leads to some leakage of material out of the black hole. And it's very weird how this happens, because you think things are just falling to the black holes and they're gone and you don't hear from them. That's it. That's the end. But Hawking showed that just quantum fluctuations lead to things evaporating. So these surfaces of no return cannot be exactly one way. And at some point, they should disappear. So then the question is, when black holes disappear, what happens to the old information assigned to them? Because nothing can go faster than the speed of light, so stuff are deeply hidden inside. And that's been a paradox, basically. And it's one of the manifestations of the quantum gravity paradox, the inconsistency between Einstein's theory of relativity and Einstein's theory of quantum mechanics, if you want. Although Einstein was not the only one who contributed to the development of quantum mechanics, but he certainly had a key role. So these two of Einstein's theories are not consistent with each other, and it's not an abstract inconsistency, the consistency that somehow is in our face because now we are observing black holes, either through the gravitational waves or through, say, Event Horizon Telescope that Professor Broderick, my colleague down the hall, is observing with the Event Horizon Telescope. So the question then is, what is at the horizon, and is there a quantum structure that really responsible for, say, Hawking radiation, if there is a Hawking radiation? Now, if there is a quantum structure, then there is no guarantee that black holes are black. I mean, we know they could emit something. If they're emitting something, then could they reflect something as well? And that was kind of the starting point of our exploration. We looked for signals that could be reflected by quantum structure. We found some evidence for it. Other groups looked for it, and some have found evidence, others have not, using different methods. And the past 5 years has been kind of both stressful and interesting, because we have been dealing with basically this new emergent field of what's happening at the horizon of the black holes. I've given it different names. I originally called it black hole ecology, which is kind of understanding of echoes for the black holes. More recently, I called it black hole seismology. I don't think any of those names have quite a stock, so we see what people will call it in the future. But it's something that now we are kind of really the two-pronged approach, which is one is trying to understand what should come out if there is quantum structure, and the other is, okay, if we do understand what comes out, or given that we don't know what comes out, what is the best observational strategy for look for these? And that's an ongoing odyssey.
My next question for you is, as a cosmologist, you constantly wonder about the unsolved problems that lay hidden within the cosmos. So what specific questions are you most interested in tackling?
Well, I wish there was one answer. I don't think, that's an ever-changing question. And if you just look at the list of things I've worked on, it's evolved over time. It's partly driven by observations. New observations come out. It's partly driven by places I've been at. Environments differ. I used to be in astronomy departments at Princeton and at Harvard. Now I have one foot in the Astro group at the University of Waterloo, another one at Perimeter Institute for Theoretical Physics, where I've been, I guess, for 12 years now. Actually, not 14 years now. 12 years at Waterloo, at university, 14 years at Perimeter. But maybe most of all is really driven by the people I talk to. And they could be everywhere. It could be you, it could be others. In fact, when the pandemic started, of course, we stopped seeing each other in person. So the online, the online meets and online meetings peaked and increased. So I managed to find collaborators who I've never met in person. So I just found them on Twitter and started talking, and that's how it happened. So and then we wrote a paper on special signatures of a particular Big Bang model that we could see in the cosmic microwave background, for example. So that's kind of the story. Is that, I mean, of course, I have my own interests. I want to get to the bottom of the deepest problems of nature, but these are hard problems, and ideas don't come along every day. But they do come along through brainstorming and through talking to others and listening to seminars, reading papers, going to lunches and dinners and things of that sort. And I don't know what the next one is going to be. I've worked on everything you can think of, from neutron stars and black holes to Big Bang and quantum gravity, and I don't know what's going to be next. And I should add pandemic to that. Yes, I've worked on that too.
Yeah, I took a look at the model that you designed for COVID-19. It's brilliant.
Yeah, and I mean, we did a lot more work on that. It's just writing that down. That was just still ongoing project. So I mean, things in quantum gravity has been 100 years in the working. So I think the pandemic modeling also may take some time.
Yeah.
But yeah, I mean, we're not. I think I'm taking the same approach to pandemic as I am, which maybe it's not the right approach, but I mean, the way I do things is just sit down and think deeply and brainstorm, and things may take a month or may take a year or may take a decade, who knows. But that's kind of the route we're taking now to addressing it.
My next question for you is, you have some astonishing ideas regarding the nature of dark matter. One of these ideas is the possibility of it being primordial black holes, in which you have
primordial black holes.
Yeah, in which you have worked with David Spergel, who is a leading physicist in the field of dark matter. So what are these primordial black holes, and what connections do they have with dark matter?
It's a very good question, and it's one that it's related to what we discussed before. So dark matter is a mystery and could be a fundamental particle like neutrinos. For some time people thought they could be dark matter. It turns out they cannot, given what we know about them, at least not most of the dark matter. There are other fundamental particles people have thought about. Axions is one idea. It's the type of a scalar field that is very light. Another one is what's people known as WIMP, weakly interacting massive particle. But since, I mean, anything can go, it doesn't have to be a fundamental particle. It could be something much more weird, and black holes is one possibility. So there are the types of black hole that we know, like the one that LIGO saw, the ones that Avery Broderick is observing with the Event Horizon Telescope. Those are big black holes, and they're made out of, or basically, we kind of have a good idea of where they came from. They basically came from collapse of ordinary matter into things that couldn't be stopped by any forces, and then they're crushed into, I guess, a singularity or something within their event horizon. But they come from standard processes, and their mass is really, we have a good handle on their mass. It's either through basic collapse of these massive stars or death of these massive stars, or through accretion into some early black holes over time that supermassive black holes at the centers of galaxies come about. Their mass is not very much. They're much less than the mass of dark matter, because we know the mass of dark matter from various cosmological observations, and there should be much more of dark matter, basically almost 5 times more dark matter than there are ordinary matter. So if you just make black holes out of ordinary matter, that cannot be nearly enough for dark matter, just by what I was saying. But if you have a different process in the early universe that could form black holes from, say, radiation in the early universe, those black holes, they are not made out of matter we see around us today. They're made out of basically pure energy that was existent in the early times. And there could be much more of them in principle. So there could be enough of them to account for dark matter. In fact, there could be even more. So if you form too many black holes, then that could be a problem, in fact, for your model. But you could just form enough of them, and those are known as primordial black holes. So you need some sort of a weird things, maybe a phase transition in the early universe. or some weird initial conditions with kind of very small scales and homogeneities that give you the right amount of black holes. So that's a model for dark matter. Now, it turns out that if these things are very big, the dark matter particles are very big, they could actually do some damage. So they could basically shake things around in a manner that is observable. If they're really clumpy and if they're really massive, what they're going to do is, in fact, they're going to mess up a structure on very small scales. Because, the standard cosmology has a prediction for how much a structure you have on very small scales. And in particular, the best way of measuring this right now is through what's known as Lyman alpha forest, which is basically, if you look at a spectra of quasars on cosmological scales, and there are places in the spectra of quasar that basically tells you that the distribution of neutral hydrogen along the enough side. So this distribution of hydrogen is very clumpy, and by a study of these spectra, you could tell how clumpy it is. So this is called Lyman alpha forest because it's a particular absorption of the hydrogen or neutral hydrogen atom. But as you see at different distances, it actually happens at different redshifts or different wavelengths. So you see basically a forest of absorption lines, basically. And this forest of absorption lines maps the structure of the universe on this very small scales. If there are too many very massive primordial black holes that make up dark matter, then your forest becomes essentially too crowded. And from observations at the time, but this was like more than 20 years ago as part of my PhD, we used that to put a limit on how crowdedness of this forest in fact constrains the mass of dark matter particle. That at the time is about 10,000 solar masses. With better data now, it's probably more like 100 solar masses. So that's an upper limit. It could be a smaller, but then there are other observations that limit kind of the lower limit on the masses. So from microlensing events, it starts getting brighter and dimmer as these go in front of you, in front of the stars. So it's kind of the space of primordial black holes making up dark matter is being constrained. They're not entirely ruled out yet. But the past 20 years, and in fact 40 years of studies have made the possibilities less and less. The space of possibilities has shrunk quite a bit in the past 20 years.
My next question for you is, what are your predictions for the field of gravitational waves astronomy and for cosmology as a whole in the future? Do you think we would ever find the unification that we're looking for?
That's a very deep question, and I don't know. I guess I suppose I wanted to say I'm not in the business of prediction, except that physicists are in the business of prediction. But in some sense, predicting the future of a field requires even more expertise that I've managed to grab throughout my my career in the past, 25 years, I would say. No, I think there will be new surprises. Gravitational wave astronomy itself was a surprise. People have been trying to detect gravitational waves for 40 years, and it's only 5 years ago that it became a reality. I think there will be new discoveries. We just need to keep an open mind and explore new ways of doing things will be different from the old ways. So I would say as long as we don't stick to doing things the old way, then there will be new discoveries. It's just we have to keep an open mind. But where they will come from, I do not know. 6 years ago, I had no idea that I would be working on echoes or gravitational waves. My main thing was working on Big Bang models and dark matter, as you know. But suddenly everything changed in, a span of a couple of months. And now most of my papers in the past 5 years have been on gravitational waves and basically probing the horizons of black holes. So So I anticipate very much and look forward very much to the next surprising discovery, and I guess I believe it's going to happen.
My last question for you, in a closing remark, Einstein once said, "I want to know how God thinks. The rest is just details." So, do you think it is really possible for us to understand the universe as a whole, or is there a limit to human knowledge, philosophically speaking?
Well, I mean, I think there are limits. There are practical limits, but then our job is to push the limits, and that's, I think, all that matters to me.
All right. I think that's everything I have for you. Thank you very much for doing this interview with me. I really appreciate it.
Thank you. It was fun.
It was very fun. Have a good day.
You too. Thanks.
Bye.
Bye.